Hey everyone, in this video we're going to be going through a full example from start to finish for how to run a CFD simulation in SU2. So the steps that we're going to take are first to define the problem, second to create the mesh, which is the .su2 file, third create the configuration file, which is the .cfg file, fourth run the simulation, and then fifth we'll analyze the solution. We'll be using the same problem that we used in my oblique shock example problem, and we'll be able to compare to the results from that one. Now if you go into the SU2 website to their test cases section, you'll note that they already have an oblique shock example problem that goes through some of the necessary steps to run the simulation and the reasons for why they set some of the settings in the configuration file, but I decided to do this video so that we could go through all the steps necessary from the start all the way to the end. So the first step is to define the problem, and here we have the schematic drawn in blue with the oblique shock shown in red. Upstream of the oblique shock we have state 1, downstream we have state 2, upstream we have Mach number, temperature, pressure, M1, T1, P1, and then downstream again Mach number, temperature, pressure, M2, T2, P2. The flow is turned at an angle theta from the horizontal, so that's the wall angle, or wall turn angle seen over here, and then beta is the angle that the oblique shock forms in relation to the horizontal. And so for our problem, similar to my oblique shock problem example, we have the upstream Mach number is 3, the wall turn angle is 13 degrees, and the ratio of specific heats is 1.4. For these simulations we also need to specify the upstream pressure and temperature, so I've said that P1 is equal to 101,325 pascals and T1 is equal to 300 Kelvin. The next step is to create the mesh that we will be solving the problem on, and so you can see here that this is the horizontal wall and then the wall that's turned at an angle theta with respect to the horizontal. To solve the problem we need to bound this and create a domain that we're going to solve the problem in, so we go up like this and over and down, and so everything that's inside the purple lines, that is the domain that we will create the mesh on and in which we will solve the problem. So the question is then, what are the locations of these points outlined in green or circled in green? We're going to call this one P1, P2, P3, P4, P5, and once we've made these and connect them with lines, that defines the domain. So we're going to start off here, and we're going to call this one P1, and we're going to say that it's at the origin, so we know that that's going to be at 0, 0. I also know that I want to just create this line length to be 0.5, so that's why we can say that P2 is at 0.50. Then to get where P3 is, I'm just going to define that this length from here to here is 1, and so we need to find the y value. So we can find that the y value is just equal to the tangent of theta, and we know theta, and so when you plug in 13 degrees into tangent of theta, we get that the y value for this point here is 0.2309, which means that P3 is located at 1.5 because of 0.5 plus 1, and then 0.2309. The last thing we need to stipulate is how high the top domain, or the top boundary of the domain goes, and so the only stipulation here is that I wanted the oblique shock to exit the right-hand side of the domain as opposed to intersecting the top boundary. So we can find the PS, which is the location of the shock exiting the boundary. We can find that using the tangent of beta, knowing that this is equal to 1 still, and so we can solve for the y position, PSY, by plugging in the beta angle, which I found using the theta beta m relation to be 30.222. Go back to my oblique shock example problem if you need a primer on that. And so that distance from here up to the point where the shock exits the boundary is going to be 0.5825. And so all you need to do is pick a boundary a top boundary that's higher than 0.5825. What I decided to do was to stipulate that this distance here is equal to this distance here, and so the top boundary ends up being at, in my particular mesh that I'll post, is at 0.9342. So that 0.4 is at 1.5 and 0.9342, and then 0.5 is simple because we're back over right above 0.1, so we're at x is equal to 0, and we're still up at that P4 because it's horizontal over from P4, so we're up at 0.9342. The next step in the mesh creation process is to prescribe boundary conditions, which are also called markers in SU2. And so here's the domain that we defined, and we'll specify some names for these boundaries here, and you can see that these are names that SU2 will associate with actual markers or actual boundary conditions in the configuration file, but you can name them anything that you want. It's just good to be descriptive. So here, this is what we want to call the inlet because that's where the flow is coming in. Here is the outlet, and then the top and the bottom are walls, which means that the flow will be parallel to the wall. They're impermeable, which means that the flow cannot cross the wall. And so the actual markers that we'll be using in the SU2 configuration file, which I'll show later, for the inlet, we're using marker supersonic inlet because we know the flow is supersonic at the inlet. At the outlet, marker supersonic outlet. It turns out all the flow at the outlet after an oblique shock or after a weak oblique shock is still supersonic. And then for the walls, we're going to use the marker Euler, and that just sets an impermeable wall. The last step is to specify the number of points used for each boundary line. Note in GMesh that you specify the number of points, not cells. So I usually specify the number of points as like 201 or 51, such that the number of cells is a normal even number. So for instance, if we're looking at the inlet and outlet boundaries, we know that we need these two to be the same number of points because I'm using a transfinite mesh in this case. So I'm saying that the left and the right boundaries have to be 201 points, which means that they're both going to have 200 cells. Now, the reason I chose 0.5 for the bottom here and then 1 for this is because this length or this cyc is going to have double the amount of cells as this one. So for here, I'm going to set it to 51 points, which is 50 cells. And if I know that I need this boundary to have twice as many cells, I'll set that to 100 cells. So in GMesh, we're going to set 51 points for this boundary, 101 points for this boundary. And then to compute how much this boundary needs, it needs to have the same number of points as the bottom boundary, which means that we're going to add up 50 cells plus 100 cells. That's 150 cells, which means we need to set this one to 151 points. I've also written a short little MATLAB code that computes those points for the mesh. And so if I run this code, then you can see the mesh pops up with the points down here for P1, P2, P3, P4, P5, specifying P1, P2, P3, P4, P5 with the expected oblique shock plotted here. And you can see that the distance up here and the distance down here should be about equal or exactly equal based off of the way that I'm constructing this mesh, and these are the values that we derived on the whiteboard. So let's bring these points into GMesh to create the mesh. Okay, now we're in GMesh, so we're going to make this mesh that we defined. We're going to go first to Geometry, Elementary Entities, Add Points. And in here, instead of clicking in here and pressing E, I'm going to define them here. And so we'll go first at 0, 0, that's 0.1. Then we're going to go to 0.50, press Add, that's 0.2. Then we need to go to 1.5 and 0.2309, that's 0.3. And then we need to go up to 0.9342, add that. And then we need to go back to 0 for the x and add that. X out of this and press Q to abort. Now we need to add straight lines between these points. So we'll click straight line and we'll click this point, then this point, and that point, that point, this point, this point, this point, this point, this point, press Q to abort. We need to make this domain a plane surface, so we'll click plane surface, click the boundary, press E, and then press Q. Make sure these dashed lines appear when you do that. Next, we need to define the boundary markers that we mentioned on the board, and so we'll go to Physical Groups, Add Line, and here we're going to name these boundary markers. So first we'll start here, and we'll name this inlet, and you have to click in here and press E, and then once it goes away from, once it turns back to blue away from red, then you know that it's set. Then we need to go over here, we'll click that one, and we'll enter outlet, and then again click in here, press E, and then all three of these lines can be wall, so I click all of them. You don't need a control click, it'll just select all of them. We'll call it wall, and then click in here, press E, and we're done with that. Press Q to abort. The next step is to create the transfinite mesh. So we're going to collapse this, collapse geometry, open up mesh, open up define, open up transfinite. First thing to do is to click surface. We're going to click the surface, the dashed lines here, and then the next thing we need to do is select the ordered boundary points. So 1, 2, 3, and all the way over here for 4. Press E, press Q to abort. Now we need to specify the number of points on each of the boundary lines, and so here, like we said on the board, I'm going to select the inlet and the outlet, and these are both going to be 201. And so we click in here, press E to apply. Then down here we said this was going to be 51. Again, E to apply. This guy here is going to be 101, E to apply, and then this guy up here is going to be 151, E to apply, Q to abort. The last thing we need to do is to recombine before we mesh, and we'll click the dashed lines, press E, then Q, and then we'll press 2D, and this creates the mesh. Now as you can see up here, this is still just the default untitled.geo file. So we're going to go into File, Save As, and I'm going to go into my grids GEO file, and we're just going to call this your mesh name.geo. It'll guess from the extension, and we're going to save that. Okay, oops. Okay, and then now what we want to do is we want to export the mesh as a .su2 file so that SU2 can read it. So we're going to go into File, and then Save As again, and then in my SU2 folder, it doesn't really matter where you save it, just know where you save it. We're going to name this your mesh name.su2. Again, it'll guess from the extension. Press Save, click Save All, OK, and it created the mesh. So now we're inside of my VirtualBox running Ubuntu, and I'm going to open up the terminal, and then we can cd into the folder where I keep everything, which is Media, SF Linux Shared, and then I'm also going to cd into my SU2 example. And this is the directory where I keep the two files. You only need two files to run the code. And so the first one is the .su2 file, which is the mesh, and the second one is the .cfg file. You might notice that I renamed my mesh file. I like to name the configuration file something specific like Oblique shock, OS for Oblique shock _ single, because it's a single shock, and I have a double shock example I'm going to be doing later. And then I name the mesh _ whatever that file is. You can do whatever you want, but that just keeps it straight in my head. So this is the third step, which is setting up the configuration file. You can download the master CFG file from the SU2 website, or you can use the one I have here that I'll post on my website. If you use the master file, you'll have every single option available to you, which is good, but also means that the file is really big with a lot of extra stuff you won't need. I first downloaded the master file and then deleted everything I didn't need from it, which shortened it down to the file that I have here, and which you can, again, find on my site. Also note, however, that the master file on the site will probably be for the newest release, and I'll just say that I'm running these simulations using version 4 because that was the current version when I was running all these cases for my videos. However, the most up-to-date version now is version 6, so if you experience any issues with my configuration file when you're using a different version, the only thing I'll say is there might be a CFG file compatibility issue. So if you want to make sure that it runs with the files I give you, download version 4. Okay, so let's get going with the actual configuration file. So this is the file here, and you can see that it's pretty long, but we don't need to go through every single value. I'm only going to go through the pertinent ones that we need for the simulation that we're running. So we're going to start off here. And we're talking about solving the Euler equations, which is why this is set to Euler. We are not restarting a solution. This is what you will set to yes if you decide to restart a solution. Right now, we don't have any restart files. We haven't run anything, so this is set to no. We're obviously solving a compressible flow because we're dealing with oblique shocks. Now, these are the compressible far field definitions. These, I believe, are used for setting the far field marker or boundary condition, and we're not using the far field marker in this particular problem, so we don't need to worry about these ones. Again, I am not an expert in terms of everything that is set in this file, but I have run enough cases where I can get the results that I intended to from setting up these files. So then we're going to go down to the ideal gas properties, and we're going to use a ratio specific heats of 1.4, specific gas constant of 287 joules per kilogram Kelvin. And then here is the important one, the boundary condition definition. And recall that they're called markers. So as mentioned before, we're using the marker Euler for the wall. So this is the actual boundary condition, and wall is what we had set in the GMSH file. And so the next thing down here is the supersonic outlet. Let's just go with the outlet first. And this one is simple enough. You just set it to the outlet marker that you set in the GMSH file. And then the last boundary condition or marker that we need is the supersonic inlet. And you can see that it gives you the format here where it's the inlet marker, and we set ours to inlet. And then next is the temperature, which we specified as 300 Kelvin. And next is static pressure, which we specified as 101,325 pascals. And then the last ones are velocity x, y, and z. We're talking about only a horizontal velocity, which is why we set the y and the z to 0. But what is the x value? We know that our upstream Mach number is 3, and so we can compute the speed of sound using the equation square root of gamma RT. So we're using square root of 1.4 times 287 times 300. And then if we multiply that by a Mach number of 3, that gives us the velocity as 1041.5, blah, 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 blah. Okay, let's keep on moving. So we're going to go down to here where it says number of total iterations. This is, like it says, the number of total iterations that it will run before it stops. I have this set to 1,000. In this case, it should probably finish in about 500 iterations if I recall correctly. Okay, now you don't need to worry too much about all this stuff that's in here. You can play around with it if you want to, but let's just sneak down to the input-output information. The first thing here is the mesh input file. This is the name of the file that we just made from GMSH, so mesh os single.su2, and the mesh input file format. You can see there's a few here. We're using SU2. It corresponds with this up here. Then the next thing is the output file format. I'm using Paraview because Paraview is open source, so you can download it for free, and that's how we'll look at the final flow solutions. The next thing down here is the output file flow, and this is where the actual .vtk, which is the Paraview extension file, will be created. And so we're going to call this just flow_os, and it'll pop up as flow_os.vtk. And then we have the writing solution file frequency, which I've set to 100 iterations, which means that it'll output a flow_os.vtk file every 100 iterations and allows you to monitor the solution. Okay, now the next step is to just run the solution. So we need to make sure first that we have both the SU2 file and the CFG file in the same directory. And the way that you run this is using the SU2_CFD executable with the name of the configuration file, so like that, and I would press enter and run it. Now usually when you install the SU2, you'll get this SU2CFD added to the path so that you can just run it like this, but let's just say that it's not added to the path. How would you find it? So I'm just going to open up a new terminal, and we will cd into documents and then cd into SU2 v4, and then we'll go into SU2 version 4.3, and then we'll go into the SU2 CFD, and then in here we need to cd into the bin, and then here you could see, since it's highlighted in green, this is the executable, the SU2 CFD. So you could always put this entire path and then the configuration file name, and that will run it. But if it's already added to the path, then what we can do is just run, like I mentioned, this SU2 CFD and then the configuration file name, press enter, and it should start iterating. Okay, now we're not going to sit around and wait for that solution to finish, but once it's done, this is what you'll see in the directory, and this is the important one right here, the flow OS. If I had it from the other folder, it would have been flow_os.vtk, and this is what we can open up in Paraview. So the next step is to open up Paraview. So this is Paraview 5.4.1, and to open the file, we're going to go up here to click the open button, and we're going to go to navigate to the folder where the solution is saved. And so we're going to find the .vtk file and double click, and that opens it, and nothing shows up, and that's because we need to press apply. And so once we press apply, then it'll pop up, and this looks something like an oblique shock. Now, if we look at what is actually being plotted here, it says conservative 1, and that looks kind of weird. And if you go up here and you click through, you can see that there's all these different variables, and you can see conservative 1, 2, 3, 4, and you might wonder what those are. Well, these are the variables that are being solved for in certain CFD codes. They solve in terms of conservative variables, and so those are also output with the solution of your normal, Mach number, pressure, temperature. Conservative 1 is actually just density. Conservative 2 is density times x velocity, so rho u. Conservative 3 is density times y velocity, or rho v, etc., etc. Now, we will come back to these conservative variables in a second, but first, let's look at how we can change this. So up here you can change it. You can change it to, let's just say, pressure, and it'll change this and this over here to pressure, but you can see that down here you can also change it in this panel down here, and then we can change it to Mach number, for example, and it'll show the Mach number. Okay, now let's say that we want to check some actual values to see if this simulation matches the analytical solutions. So here in my MATLAB program, I just have some of the solutions here, and you can see that the downstream Mach number is 2.356. The pressure ratio is 2.4937, the temperature ratio is 1.3269, and then the actual downstream pressure is shown here, and the actual downstream temperature is shown here. So how can we check those values in Paraview? Well, let's go over here, and then up here you can see that it'll split the screen, and we're going to create view all the way down the bottom, spreadsheet view, and then up here we're going to select this button right here which says show only selected elements. Okay, now there's nothing there. So if we go back into here, into this window, press D on your keyboard and it brings up an arrow, we can click. And at that point we can see that it shows some of the values, all the conservative values. And if we scroll over, we can see the Mach number is 3, that's our free stream, that's what we set. Pressure is 101.325, temperature is 300. So those are the values that we set. That's obviously going to be good. So let's just move on to where we actually care about, behind the oblique shock. So we'll press D again and click over here. It changes these values, and you can see now we have the Mach number of 2.3547, which is close to what we had, and the pressure and temperature are also close to the downstream values from the analytical. Okay, now let's X out of this spreadsheet view to bring the full screen back up into here. And so another thing that you can do is up here you can see it says surface. We can also put in surface with edges, and this will show the actual mesh that we were using for this simulation. it takes a little bit longer to move things around, so I'd usually just keep it with surface, but that's just to show you what mesh we were actually using. Okay, and the last thing I'm going to show you in this video is streamlines, and so that is this button here, and it looks like it's grayed out, which is not great. This is the stream tracer button. So how do we actually get streamlines? Well, we need a vector in order to get the streamlines. We need the velocity vector, and we don't have that right now. But if we go back to the conservative variables that we had, remember row 1, or conservative 1, conservative 2, conservative 3, we can construct the velocity vector from those. So what we're going to do is we're going to select the actual VTK file here. That's what we're looking at, the solution file, and we're going to click this. This is the calculator button. And it brings up this down here. So what we're going to do is we're going to name this, instead of result, we'll name it velocity. And in here, we're going to create this velocity vector. So first I'm going to open parentheses. Now we're going to go look into scalars. And these are all the scalars that we have, right? We don't have a vector yet. So we want to create the vector ui plus v, or ui hat plus vj hat. That's the velocity vector. So how do we get u? We know conservative 2 is rho u. We know conservative 1 is rho. So we can take conservative 2 and then divide it by conservative 1. Close that. That gives us u. And now we need to say times I hat. So that is u I hat. Now we need to plus, open parentheses. Now we need v, so we can take conservative 3 divided by conservative 1, close that, times j hat. That is the velocity vector, and we can apply. Okay, and now with the calculator selected, you'll note that the stream tracer is available, or is an option to click now. So we can click that, and this gives us our initial line. And so I actually want this initial line to be something like a vertical here. And so if we go down, we can set the exact values where we want to start at 0, and we're going to go up to, you know, it was 0.9 something, or sorry, 0.9, right? Something like that. It doesn't really matter. It goes, you can put it up to the top boundary. And so this says it's a high resolution line source. That's how it's seeding these particles for the streamlines. And the resolution is how many lines you're going to get. 1,000 is a little overkill here, so let's put in like 20, and then we will press apply, and now you get these streamlines, but it's turned off the actual flow field, so let's turn that back on again, right? And then we can go into stream tracer, and I don't care to color these with anything special. Right now it's coloring it with respect to the density. Let's just change this to solid color. It'll turn to white, and now you can see the streamlines which follow the path of the flow. So here upstream of the oblique shaft they're going to be horizontal, and then downstream it makes sense that they are now parallel to the wall. So that is the start to finish tutorial of how to run a CFD solution using SU2. Thanks for sticking it out. Hope you learned something new, and thanks for watching.